Okay, let's do a problem set which is very similar to the one in the previous video, and the only difference is that this time we have for each group 1, 2, 3, 4, 5 observations, but we still have 3 groups. Okay, so below table summarizes the scores of 3 players A, B and C in a bean toss competition. So here's the data. Please conduct an ANOVA analysis test. The null is there's no difference among the 3 players. There is at least some difference. Okay, so what we could do is we just can copy and paste that into Excel and work from there. So that's what I will do. So I'll just open Excel. Let's paste the data here. Okay, so what we need is the total sum of squares. We need the sum of squares between and the sum of squares within. And so the total sum of squares is equal. So first what we need is we need the grand average of all the observations. So I call that grand average. Okay. So now we just tell Excel, please give us the average of all those 2, 3, 4, 5, 15 observations. Okay, so that is 16. So now the total sum of square is, so what I do is I'll just subtract from every observation the grand average of 16. And square it. So now for the first observation, we have here between 10 and the 16, it's a difference of 6, so 6 squared, 36. And now I just can copy down the formula 2, 3, 4, 5 times. And then I copy down, and then I copy it to the right. Control R copies to the right, Control D copies down. And now we have always calculated from each observation in our table with the original data, we calculated the squared difference from the overall mean. So now, so the total sum of squared is equal to the sum of those observations. So that's 462. Okay, great. So now we are done with this one. Oops, maybe I should have removed the formula. Control copy, paste special 1, 2, 3. That copies only the values. Okay, so next let's calculate for each group the group average. And we don't need the grand average anymore. So group average and that is equal to the average. So the group average of all the observations in A, okay, that's 11. And let's copy that to the right. So then we have 11, 16 and 21. So next what we need to do is we need to calculate the sum of squares within each group. So that means each observation within each group. From each observation within each group, we subtract the overall mean. But now you see I only anchor the row because I want to copy that formula to the right. So I just put a dollar sign in front of the 7. So B7, that is where I have my group average for A, and then we close parentheses and then square it. Okay, so the first observation for beam player A, it's a 10, the average is 11, so the difference is 1 squared. And again, I copy this now, 2, 3, 4, 5, 4 times down. And then I see there's like a total sum of 4. And now I can copy that to the right. Okay. And now we have all the sum of squares within each group. And the sum is 212, which we can see down here in Excel. So 212. Then I know that the sum, actually that was the wrong, 212 goes to the sum of squares within. So that means that the sum of squares between the groups must be the 462 minus the 212. Okay, so those are the sum of squares. And to be more consistent with an ANOVA table, I'll actually put the total sum of squares on the bottom. Okay, so now we have here sum of squares between, within, total sum of squares. Okay, so now we need to have the degrees of freedom for each group. The degrees of freedom is if we have 3 groups or 3 players, then our degrees of freedom is 3 minus 1, so in that case that's 2. But we have 15 observations, 3 times 5, and the degrees of freedom is n, the total number of observations, minus the number of categories or players, the A, B, C, so that's 12. Then next we calculate the mean sum of squares. So now we have to divide for the sum of squares between the groups, the 250, over the freely variable or varying degrees of freedom divided by 2. So that's 125. And the sum of squares within each group is, I copy down that formula, 16.67. Okay, so let's maybe display only 2 decimals. So that means our F statistic is F stat is equal to the 125 divided by the 17.67, and we get 7.07. Okay, so then what's the p-value? And the p-value is equal to, so now we use the command f.dist right-tailed, and then we see Excel wants to know the x and then the degrees of freedom on the top, and actually you can't see the formula, so let me see if I can put that a little bit to the right. Okay, now we have a little bit more space, equals f dot dist right tail. Okay, so the x is the 7.075, our f statistic. The degrees of freedom that we have in the numerator, that's degrees of freedom 1, that's 2, and the degrees of freedom in the denominator, that's the 12. So now we get the p-value of roughly 1%. We could also calculate still the critical t, but as you can see in the question, I didn't give you an alpha. So commonly we would use an alpha of 5%, but because we already know that our F statistic is even significant at an alpha of 1%, yeah, we can calculate two critical values. Let's call that F critical, maybe 1%, 0.01, and F critical 0.05, and that is equal. So now we use the formula F dot inverse, right tail, and the probability is 0.01, and again degrees of freedom in the numerator and denominator, so that's 2 and 12. So now we should get a F statistic which is actually very similar to the 7.075, but probably slightly below, which is 6.9. And we can see that our actual F statistic is also in the rejection zone, and then of course the critical value for a 5% alpha would be 3.885, so we definitely reject. Okay, so I hope that this clarified how we do a ANOVA analysis of variance. So we clearly reject the null hypothesis that there is no difference between the three players, and if you look at the data, it looks like that player C is definitely way better than, for example, player A. Maybe the difference between A and B is also significant. For this we would have to do a 2-sample t-test, but yeah, that would be a different story. So let's focus on ANOVA. What it tells us is, yep, there's definitely a difference. Okay, so last thing I want to do is we just go back again to data analysis, and we do ANOVA, and again we only do a single factor. So a 2-factor would be, let's say they play the competition in the morning and in the afternoon, and then the question might be, is there a difference between playing in the morning and the afternoon as well? Yeah, the spirit is the same, but once it comes to many different factors, you slowly migrate towards using other techniques, especially regression analysis. So this is good enough to get an understanding of ANOVA. So we say ANOVA single factor. Again, we have labels in the first row, and our data A, B, C is grouped in columns. So now we just highlight the data, the 5 observations, so not the group means. And then I just want it somewhere here so we can compare it with what we did manually. Okay, so now what do we get? So we have the same sum of squares, 462, 212, the degrees of freedom, 2 and 12. Then the mean sum of squares, so that is all the same. So if we let's just okay, so our F statistic is 7.075. The probability, the p-value, the probability of having made a type 1 error is less than 1%. The F critical is 3.885 or 5%. So we reject the null hypothesis that there is no difference between players A, B, and C. Okay, so that concludes ANOVA. It's not that complicated, not that difficult. There's a lot of intuition to it, I feel. And yeah, let's just stop here. And yeah, then let's start something else now. Hope that was useful, and thanks for watching.